Okay, good morning, everybody. Welcome back for this new session of our school. It's my pleasure to let Veronica start this morning session with the fourth lecture.
Thank you very much. Okay, so yeah, today, at least for the first lecture, we will start with an exercise. So finally, we will see our example, the equation that also appeared at the very beginning, which is the modified Bessel equation with parameter m on n. And again, let me maybe start by recalling that the overall goal was of this mini course was to see different way to compute, to find solution of differential equation. And this was somehow our map. So we have discussed these two methods, A and C. Finally, today we will see also method B. And we have also seen other slightly different subject like Borel-Laplace summation, which is what allows us to go from formal to analytic, but in fact is not only for solution of differential equation. It works much more generally with that when we have divergent power series. And we have also seen yesterday that, in fact, the Stokes phenomena, which is something that characterized differential equation with the regular singularity, can be also understood geometrically, and we have seen it quickly through these symbol integrals. And so today, as I promised, I will do the exercise, part of the exercise I was mentioning during the course, and in particular for this example, we will see the free method, and then the second part instead will be a bit an introduction of resurgence. So why I choose this equation? Maybe I should have probably said it a bit more at the very beginning. So the first remark is that if you choose m on n, maybe n equal to 1 and n equal to 3, this is after a change of coordinate related to the Airy differential equation, which is very much studied. That is one of the typical examples you encounter when you study Borel summability or resurgence. This is slightly more general, but at the same time, it's not just a generalization. It's also interesting because, again, after a change of coordinate, solution of this equation are known as Airy-Lucas function. And these functions here are the one studied by some people that wrote exactly this paper. I just quote you can Google this title. So it's Shift-Witten class and topological recursion. So this is somehow a place where equation like this, in particular solution of this equation, have been studied. But okay, so let's start with the exercise. The first method I would like to study is the first one, so the Poincaré method. How do we find this solution of this equation? Formally. So what is the polynomial p? The polynomial p, we read it from there, is the part without power of 1 on z. So it's just this z squared minus 1. And we have to look at the root of this polynomial. Nothing but plus and minus 1. And now we have to compute tau. So remember that tau lambda is q of minus lambda divided by p prime of minus lambda. Who is q in this case is just this dz. So q minus lambda is minus lambda. And who is the derivative of p evaluated in minus lambda? Well, the derivative is just 2 dz. So it's 2 minus lambda. And so what you get is 1/2. And in fact, it doesn't even matter whether it's lambda plus 1 or minus 1. This power is the same in both cases. And what the Poincaré algorithm tells us is that we will have two solutions, the 1 and the minus 1. So here you have minus lambda z, and z to the minus tau, which is minus 1/2. And then you have to take an ansatz k 0 to infinity z minus k. And here, it's similar. Let me call the coefficient zk prime. We have to determine this coefficient. So how do you do? Well, you take the solution, you plug it in here, and then you solve recursively for the coefficient. And you can also do it numerically. For instance, if you use Mathematica or other computer program, you can see how this coefficient look like. And I will just write for you the solution. So the AK is minus 1 to the k. And then you have, I will tell you what this notation means. So there are some brackets with a lower case, with a lower kappa, k here, 2 to the k, k factorial. And the other one, it's essentially the same without the minus 1. So I can also write it like this. So what is this bracket? The bracket A is essentially a ratio of gamma function. So in particular, what you see is that, so here you have morally 2 gamma function, and the gamma function grows as k factorial. So you have 1k factorial, and here another k factorial. So in fact, the growth of this coefficient is k factorial, which means the series is divergent. So as we expect, both these series are divergent. And of Gevrey type 1, because you are left with just 1 factorial coefficient. Okay, so this was the 2-formal solution using the Poincaré algorithm. And now what we learn is that if from this we want to find an analytic solution, one way is to take the Borel-Laplace sum. So first step, take the Borel transform. This is what I will denote by lowercase phi. And since we have this exponential with minus 1, the natural coordinate will be zeta 1. So what is zeta 1? Is zeta minus 1. It's a choice of coordinate. And how does the Borel transform look like? Okay, so we took into account the exponential. Now the fractional, we can just take it everything together. So maybe this is the Borel transform with respect to z of phi tilde 1. And so what does it, is the Borel transform of this series. And I put together the z and the z minus 1/2. And so the Borel transform is formal, and it passed through this linear, it's linear. So essentially, we just look at what the Borel transform does on z. And so we get AK, and the Borel transform, where we have this shift by 1/2, is given by zeta, sorry, and here is missing the exponential. So it's zeta 1 to the k minus 1/2 divided by the gamma of 1/2, k plus 1/2, sorry. Okay. Now, if we look, so this is now we have a finite radius of convergence because remember, 1k factorial, 1k factorial, 1 is here. this is another k factorial. So now this series has a finite radius of convergence. But in fact, since we know the coefficient explicitly, we also know what is the sum of the series. So what yesterday I was calling phi at 1, in this case, it's just an hypergeometric function. So it's up to a constant is zeta 1 to the minus 1/2. I take this coordinate out, and then it's the Gauss hypergeometric function f(1) with coefficient given by 1/2 minus m on n, 1/2 plus m on n, 1/2, which is the one that appears here, and zeta 1. Zeta 1 divided by 2 minus zeta 1/2. Okay. So this is what you recognize. Essentially, here it's really an equality, because you know that this hypergeometric function has the following Taylor series. Okay, now let's look at this solution. In particular, what we want to understand is whether or not we can take the Laplace transform. Because now we are in the position domain. We have taken the Borel transform. We have already taken the sum. In this case, luckily, we know what the sum is. So where are the singularities of this function? Here you see a square root. So this is not really a singularity. This is what tells you that you have to think of this function not just on the complex plane, but on the Riemann surface of the square root. And this is the point that yesterday at the fall I was doing in this way. So let me just make the picture of the position domain. So here we have 1. This part here tells you that you have to remove this cone. Oops. And what about the hypergeometric function? In fact, we know that the hypergeometric function has a singularity where the argument is equal to 1, as a branch cut singularity where the argument is equal to 1. So there is another singularity that comes from here. So this is analytic everywhere except, so it has a log, a branch cut singularity at minus zeta 1/2 equal to 1. Minus zeta 1/2 equal to 1. So what is minus zeta 1/2 equal to 1? If you do the computation, this gives you zeta equal to minus 1. So if this is minus 1, we have to take, we have to cut this branch cut, and then everywhere else this function is analytic. And so you may recognize a picture that we saw yesterday, the domain that I was calling omega lambda, in this case omega 1. Now, if we do the same for the other ones, for phi tilde minus 1, the only thing that changes is a sign. And here the exponential is in z and not in minus z. So in fact, what you will find out is that phi tilde minus 1 and let me just write the one with the at, is morally the same. So it's a constant. Now, the natural coordinate is zeta minus 1. And you have the constant, zeta minus 1 to the minus 1/2 times the hypergeometric, which has essentially the same coefficient. So sorry, I just copy and paste here. So you have 1/2 minus m on n, 1/2 plus M on n, oops, 1/2 again, and the last one, we don't have the minus sign anymore, but we still have the 2 to the k. So here you have to continue. And so once again, you can ask, okay, where are the singularity of this function? Now, zeta minus 1 is zeta plus 1. So in particular, we have to remove here the same. We have to make a cut now in minus 1. And where this hypergeometric function is singular, once more when zeta 1, so when the argument is equal to 1. So zeta minus 1/2 equal to 1 is zeta equal to plus 1. So this is the branch cut singularity of the hypergeometric. So now this time we have to cut in this direction. And we see that the other domain is the domain omega minus 1. Okay. So is it fine so far? So we have computed our true resummation in the Borel plane of the initial divergent power series. What we are supposed to do now is to take the Laplace transform. So this function now are analytic again in this very large domain. And so we can take the Laplace transform, and in fact what we would like to compute is the Stokes constant. So phi 1 plus and phi 1 minus 1 plus. We have to pick two directions in this domain where both are defined. So for instance, we can go in the theta, we can pick an angle theta and take these two contour. So this will be theta plus. So what is, in general, what is phi lambda theta? This is the Laplace transform at zeta lambda in the direction theta of phi at lambda. This was our definition. Okay, where we integrate along this ray. And we want to compare them with the one for negative theta. So phi 1 minus and phi minus 1 minus. Okay. So how do we do? Well, we have the definition of the Laplace transform, and now we know what to integrate. So let me just do in the direction for this theta minus. Maybe let me just put some color again. So this one, the plus has the branch cut here, and the minus one, sorry, not the plus, the minus one has the branch cut there. So in particular, the first one is analytic when you, it's analytic in this region. So if I go from theta plus to theta minus, phi1 plus is the one that doesn't change. I don't know if it's too messy here. Maybe we can, either you can draw it into separate plane. But remember, it's still written there. Phi1 at has only the branch cut at -1. So across, if I move the contour from here to here, I'm just crossing the positive real, and this function is analytic. So in fact, it doesn't change essentially. What about the other? As we were noticing yesterday, if I try to deform this contour, I jump into this branch cut. And so let's see at the level of the Laplace transform how we can compute this jump. So what we have to do is Laplace theta plus of phi minus 1 at minus the other one. We look at this difference. It's the integral from -1 to plus infinity ei theta plus of e minus z zeta. And now I have to copy phi at -1, which is there. So we have up to this constant zeta minus 1 to the -1/2, and then the hypergeometric. Okay. And then minus the other one. Okay. So essentially, you copy the same. I mean, I'm copying the same, but in fact, oops. The two functions are defined in a sense into different regions. Okay. Why I'm saying the two functions are defined into different regions? Because this one has a branch cut here. So in particular, you can look at, if you want to compare these two, you have to look at how to do the analytic continuation of this function across this branch cut. And luckily, for hypergeometric function of this type, we know a lot of information. So that's one example in which we can really do the computation, even by hand. And in particular, if you look at DLMF, so this digital library of mathematical function, and in particular is one of the first equation, which is 15.2.3. This equation tells you how to do the analytic continuation of an hypergeometric function across the branch cut. So now I don't want to, let me just copy this part, but then I will not, I just put some A, B, D, and then the zeta minus 1. So there is a formula that tells you how this thing jump across the branch cut. So if you go slightly above and slightly below, maybe I can just remove this guy, zeta minus 1 minus 1/2. The formula is for a generic parameter, but then we will substitute ours. So, okay. This plus I0 minus I0 really means slightly above, slightly below the branch cut. The equation that you read is the following. So you have a 2 pi I divided by gamma of A, gamma of B, and then you copy and paste this zeta minus 1 to the minus 1/2, and now there is a zeta minus 1/2 minus 1 to the D minus A minus B, and then another hypergeometric. which is with coefficient C minus A, sorry, C, D minus A, D minus B, D minus A minus B minus 1, and 1 minus zeta minus 1/2. Okay, is it readable? So you see, what this formula is telling you is that if you want to do the analytic continuation of the hypergeometric, which is defined above across this branch cut, you get essentially this extra hypergeometric function, where the coefficients are slightly different, and you have this shift. So,
plus I0.
Yes, it's plus I0 and minus I0, which means slightly above, slightly below the positive reals. And now, okay, if we just look at what A, B, D were before, and we see how this function look like. So let me just, I will keep this gamma A and gamma B for a second. So what do we get is zeta minus 1. This guy here is zeta 1/2 minus 1/2. If you take the sum of A and B, since you have this M and N, essentially they cancel. So you just get 1/2 minus 1. And then the hypergeometric has coefficient M on N minus M on N, 1/2, and minus zeta 1/2. So it's not too different. I mean, this hypergeometric really look almost like this one. And in fact, I mean, the only difference, okay, is in the coefficient, in particular the first two, and in this 1/2, which is just a constant, and this part. So if we look at these two, there is, again, another expression for the hypergeometric, which tells you that, in fact, you can put these together. And an equivalent way of rewriting this hypergeometric is 2 pi I, gamma A, gamma B, zeta 1 to the minus 1/2, and then exactly what is written here. So up to this constant C, you get phi 1 at of zeta 1. Is it readable? So this is like what you get putting together and this again is another formula that you can read from the LMF. Now here we are using the 15.10.11, okay. It's just a way to rewrite this hypergeometric function. And now this square root, in fact, help us to reabsorb it and write it with this coefficient. But so what we have understood, if we go back to our Laplace transform, so we were there. Here we just start looking at what was inside the Laplace transform and understand how to do the analytic continuation. If we use this expression and we plug it back here, or maybe there, what do we get is the following. So from there, so instead of the first integral, I use this equation. And so morally what I get is the integral from -1, and I push the contour down. So I got the integral again from -1 to ei theta minus infinity, e minus z zeta. And then I have my constant c that goes with the second term. So okay, you have c zeta zeta minus 1 minus 1/2 f(1) of, okay, 1/2 minus m on n, 1/2 plus m on n, 1/2 zeta minus 1/2 in this zeta, and the other one is this plus 2 pi I gamma A gamma B, and then this phi1 at zeta 1 d zeta. So all of these goes together inside the first integral, and then you have minus the other integral, which is this -1 plus infinity, and essentially you get the same thing. So you get c e to the minus z zeta. I mean, the thing inside is just phi minus 1 at. I don't have to recopy. And so you see that these and these cancel out, and you are left with just any up to this 2 pi I. Now let me write what is gamma A and gamma B. This you can compute it with Mathematica. So in fact it is pi cosine of m on n pi. This is this constant. And then you are left with the integral from -1 to ei theta minus infinity, e minus z zeta, p1 at zeta 1 d zeta. What is this guy? Is nothing but the Laplace transform of phi1 minus. So up to this constant, which is exactly what we will put here, 2i cos m on n pi and 1. I was computing the diff. So we are left with just this block. This is nothing but, something is missing, the constant c, but okay. This is not, I just put it. This is phi 1 minus z. By definition, is the Laplace transform. It's true that here the contour is shifted, but again, is analytic. And so this is the way you can find, in this example, very explicitly, the Stokes constant. Okay. In particular, you see that for the choice of the area function, m on n, it's 1/3, so you get 1, you get I as a Stokes constant. And if you take, for instance, m equal to 0, you get a 2. Yes. Okay. Do you have any question? Was it okay? So if this is how we compute the Stokes constant using the analytic continuation and essentially the Borel-Laplace transform. Now, a bit more quickly, we are going to see the method C. So how to do it analytically. So what was the method C about? Well, now we have to change ansatz. We start, first was the Poincaré ansatz. Now the ansatz that we take is already a Laplace transform of a certain function phi minus 1. If you take this and you plug it into the equation, so remember from ODE we will get an integral equation, and in this case the integral equation looks the following. So you get this is what comes from P. Then you have the integral from -1 to zeta of t. This comes from Q. phi minus 1 t dt, and then you have the part that comes from m on n square, which is zeta minus t, because you have a 1 on z square. And then you have this one. So this is our integral equation. This is the operator p at minus 1. Okay, now from this point of view, maybe it's not immediately clear what this equation looks like. But remember that we have proved it admits a unique solution in a certain function space. Now, since our tau lambda is 1/2, we can use one of the results I was mentioning, and so in particular, we can turn this equation into a differential equation, and phi minus 1 will be a solution of this integral equation if and only if it's also, if and only if it solves the associated differential equation. By associated differential equation, I mean you take derivative in zeta until the integral disappears, and in this case, you have to do it twice. So if you take twice the derivative, what you get is the following equation. Second derivative plus 3 zeta phi minus 1 prime, phi minus 1, so what is this phi? This is essentially equivalent to p at minus 1, phi minus 1 equal to 0 after taking derivative, after differentiating twice in the zeta. Again, maybe this equation is not yet super explicit, but remember also that we want to find a solution in not the coordinate zeta, but the coordinate zeta, in this case, minus 1. So if you use the fact that zeta minus 1 is zeta plus 1, and you rewrite the equation, what you get is zeta minus 1 times zeta minus 1 minus 2, p minus 1, zeta minus 1 minus 1, first derivative, plus 1 minus m on n square, p minus 1 equal to 0. And now these look like almost as an hypergeometric equation. In fact, it's enough to, again, introduce the following coordinate, psi equal to zeta minus 1 on 2. And if you write the equation, you find the following hypergeometric equation. So it's 1 minus psi, phi minus 1 double prime, and then you have plus 3/2 minus 3 psi. And then here I just split it into factor, because if you open again the DLMF, always chapter 15, you see that this is an hypergeometric equation, and you can find you have different ways to express the solution. But remember that our goal was to solve this equation in a certain function space. So what our existing theorem tell us that this function is in zeta minus 1 minus 1/2 plus something which is more regular. So this is what we are aiming for. So among all possible solutions that you find of this equation, you need one which has this behavior. And in fact, you find it. It's in the list. And this is the following. So it's the one at 15.10.12. And it is given, maybe you might already know how, zeta minus 1/2 to the minus 1/2. And then you get a Gauss hypergeometric with the parameter 1 minus 1/2 minus m on n, 1/2 plus m on n, and this. So it's not a surprise. Essentially, you get something which up to maybe some constant is in fact proportional to what 1 minute ago was called phi minus 1 at. This is essentially the content of our last theorem, the way we compare method A and method C. if you look at other solution of this hypergeometric, there is also another solution of this hypergeometric which has not this fractional behavior. So somehow you really, what we want is a solution with this behavior to compare it with the other one. Otherwise, the argument will not work. Okay. Now, let's see, let's discuss briefly the Stokes phenomena. So here we have seen one way. And now I want to show you what happened with the, it's dead, okay. Maybe I erase this part. We just keep this matrix there. So let's see the Stokes phenomena from the symbol picture. And talking about the symbol picture, remember that yesterday I was introducing this function, this integral. So Tn T U m minus 1 tvt. And let me just give it a name. Let me call it k m on n z. So up to a constant, this is one of the expressions that you find, again, in DLMF under the name of modified Bessel. DLMF, this is modified Bessel equation. Yeah, under modified Bessel function, sorry. And these two are Chebyshev polynomial, the T and the U. Ah, good, okay. Let's see. Larger. Yeah. Ah, yes, okay. You can yes, you can share the link. So what is this? This is it's called Shader Toy. It's a program that my collaborator, in fact, did it. So what you see here on the right-hand side is the code he wrote to make this picture. And it's open source. If you look at the link, then you can, you can play with this picture, as I will do it in a while. But so what is drawn, these two contours, the dark and light blue, are essentially some suitable contour for this function. So what you see here, there is a 3, which is maybe not super clear, but so the number 3 here is the n. So how do you make this picture? As I was saying yesterday, this contour C, maybe C, okay. You might have more, but you take the so C is given by the pre-image is Tn minus 1 of the ray which start at the critical point. So from, let's call it the K critical point is Tk plus R positive in some direction. Oops. So these are the, okay. These are the T in there. So these contour blue are essentially computed in this way. So it depends on n. If n is free, you get these two pictures. One is passing through one critical point and the other one through the other critical point. Let me also make, so where does this picture live? This lives in the T plane. So you have your map Tn goes from C coordinate T to C to the coordinate zeta. So is this map here. And so the critical, this Tk is Tn of Tk. So for each critical point, Tk critical point, you have a critical value. In this case, should be 1 and minus 2. You have 2, 1 and minus 1. And what is drawn, and then in the image, this is zeta, The dark and light region that you see there are what corresponds to the upper or lower half plane. So you choose a direction theta, you take a ray, and then you take the pre-image. And the pre-image of the ray looks something like that. So, okay, it's going in some direction. Let's do it this way. Okay, this is one of these contours, C1. And similarly for the other one. And now you can move. So here, I will not move the background. So the background is kind of fixed for a certain value of theta, which is this 0. Where is it? 0.8, but okay. You start moving, and what you will see, what I was trying to do, oops, okay.
But when you move, sorry, which parameter?
Is the parameter, it's like the argument of Z. So it's this, I'm changing the endpoint of Tn. The point is that the very dark region should be the region at infinity. So if here I have a region at infinity, sorry, maybe like this, here I take, but when I move this black thing, it will not change. I will not move everything, so they just stay as it is. But you see the symbol, oops, and you see that if you approach, at some point you cannot really make the picture. I mean, there is a critical angle, and the two flip in this way. And you can also go the other way, and you see the same behavior. So this is for n equal to 3. But in fact, you can change this number and put, oops, if I manage. So if you put 6, I don't know, you click play. And now you see that you have more critical points, because now you have a polynomial of degree 6. So you have the 6 critical point, the 5, 1, 2, 3, 4, 5. You can check by solving the equation that no matter which n you take, this is a solution of a second order differential equation, and we always find only 2 critical values. So this point here, this is the image, is Tn of Tk. And the two colors, the dark and light blue, is what distinguish between the symbol whose image is this ray, and the symbol whose image is the other one. So here I don't have the dark blue, let's make the dark blue pink. This is what distinguishes the color. And again, you can start moving them, and you see that in a sense they jump all together in a similar way, and similar from the other side. So you reach a critical point, and then they swap. So that's one way. And here there is something written in Mathematica, not by me, but by Alessandro Giacchetto. Here I want just to show you how you compute this number in a more, how can you get really something here? So this is the first example. You have a bit of parameter, but for r equal to 2, this is the area. And what is plotting are the two bases. So what I was saying yesterday, in this, maybe let me just erase something here. So these are contour plots made with Mathematica. So what's happening there is the following. You have the zeta plane, which is not drawn there. Again, you have the two critical values, 1 and -1, for n equal to 3. This is what corresponds to theta plus, and then we have theta minus below. And to understand, so we can take the pre-image of the two up and the two down. You see the picture, maybe, I'm not sure how visible is it. There is a bullet there and a bullet there, which corresponds to -1 and 1, which are the point here. Using the choice of normalization of that function. Okay, so you take the image. If you want to compute this intersection, what I was saying yesterday is that you have to take the dual basis. So you have to rotate by an angle pi this angle here. And what you see in the picture to the right is precisely what corresponds here to the pre-image of this guy and the other one. So what are these? So you take the pre-image means you take T3 minus 1 of the Poincaré. Let's give it L1. And you intersect with the T3 minus 1 of the dual. Maybe this is L minus 1. This is L1. Let me write dual, meaning rotated by angle pi. So this is L1 dual, and this is L1. And you see that they intersect once. Now, this was one example, and okay, oops, here there are even more. Here is just reversing the order and so on. Here is changing the power, so morally is increasing the power of this polynomial. And you can always see a bit qualitative if you want, but like how many intersections you have. Let me just mention about the other example of yesterday. So this is for this type of function, where you have the Chebyshev polynomial. But yesterday I also mentioned the Bessel zero, which is again, a solution of the differential equation, but it doesn't have an integral representation of this form. So if you take Bessel zero, this is essentially a solution of our equation star with m on n equal to 0. Morally, you should think of this as sending n to taking m equal to 1 and n to infinity. That's why it doesn't have this representation. But so k0 of z can be still represented as an integral. And the function that you have is z of minus 1 on t plus t on t. Okay. Maybe there is a minus sign here. From 1 to infinity. Okay. So this is Bessel zero, and what is the main difference now? This function, so our f of t now is 1 on t plus t. So it's not anymore defined on C, but on C star. So it goes from C star to T. And notice that also the one form here has this pole. But in fact, on C star, this is perfectly holomorphic. So it's fine. So nu, which is dt on T, is holomorphic on C star. Okay, now if you look for, if you try to check what's happening, so again, you can ask, you can try to understand the Stokes phenomena in this example. Let me go first here to show you the, okay. From the previous program, you can, you see here there are many options. So before we were in Ari Lucas, now we are in Bessel zero. And you see that, okay, maybe it's not super clear. The coordinates that are used there to make the plot are not this one, but you can are the exponential coordinates. So you can rewrite it using hyperbolic cosine, and that's what look like. You still have two pre-image, one which corresponds to the ray from 1 to infinity, and the other one is another solution of the modified Bessel. So once more, you have pre-image of these 2 points. And here, it's a bit more tricky to understand what's going on because, I mean, you still see that you have the exchange of the two. And you have more copy because the picture is done in this other coordinate, so as an hyperbolic. So from here you see that there are jumps, but maybe it's hard to see what is the Stokes constant. But if I open the notebook and we go here, so you see the function. Oops. The function here more or less look like what if you put r equal to 2 now, you get something which look like this. Is in the coordinate h bar, but that's not really important. And if we look at the symbol as the symbol intersect, this again is always the same procedure. Take the pre-image now with this function of some ray like this, and intersect the dual picture. And now if you look here, how many intersections you see? Well, 2 intersections, 1 and 2. That's not a big surprise. If you put m on n equal to 0 here, you get 2 up to this I. And before, if you would have chosen the point, as I said, m equal to 1 and n equal to 3, you would get 1, which is the area. So maybe the very last thing that I want to mention is it seems probably that the only thing we need to make this picture is the function Tn. So what is the role of this um minus 1? It seems that no matter which m you pick, you always get the same intersection, 1 intersection or 2 in this case, but it seems a property of the function T and not of the 1 form. From the picture, you can't really tell, but in fact, what the role of this is precisely what tells you which correct number you get. So qualitatively, you would expect 1 solution, 1 intersection, 2 intersection, and so on. But it's important to keep track also of the role of this function to get the correct number. And here, and in fact, so not here, but if you try to do the following exercise, so if you try to do the same, almost the same example, so you still take let's say the third Chebyshev polynomial, and then you take dt on t, so you slightly modify the area function, changing the 1 form. Now, t3 is always defined from c to c, but now the 1 form is not anymore holomorphic there. And adding this t here really change the picture you will get. In particular, this is not anymore a solution of the Bessel equation. It solves a degree 3 differential equation. And you can check that, in fact, being on C star really change what we have discussed so far for the area. So it's not only this function is important, you really have to take into account also the geometry of the manifold the integral leaves. And maybe the very last thing I'm gonna say in this last minute. So, okay, I hope this stuff with the picture is clear and maybe a little more visible from there. Let me mention one last thing about the Stokes phenomena. So, okay, we have seen how to get the formula. We have seen some picture. But in fact, even from the very beginning, when we compute this constant using the difference between the two Laplace transforms, in fact, what we have used is not really that we were using, that they were computing Laplace transform. I mean, this number and the fact that you have that this solution C, the other one, is already something that you see at the level of the Borel plane, of the position domain. So what I mean is that if you remember, we have this phi 1 at, phi minus 1 at. They were the two hypergeometric, and we did the analytic continuation across the branch cut. And so morally, what we have seen is that phi 1 at, now in zeta 1 plus I0 minus phi 1 at in zeta 1 minus I0, this was proportional to the other one at zeta minus 1. So what is the moral of the story here? Is maybe it's equal to a constant. Let me call it S minus 1. So the moral of the story is that essentially this is the Stokes constant, maybe up to some normalization. And this is what is telling us that phi 1, or the other way, see the other solution. So the message is that if we want to understand the Stokes phenomena, it's not really necessary to go up to the Laplace to take the Laplace transform. This is already visible from the Borel plane, or from the position domain. And in particular, like looking closer to the singularity, of phi at lambda, you find not only the information about the Stokes constant, but also the information about someone else. So a priori, you could find a different function. And this is really what characterizes resurgent function. So this is one of the features of resurgent function, which you can understand already looking at solution of differential equation. So looking at closest to singularity, you find the two things. One is the information about the Stokes constant, but also maybe a new function, which is the other one. Okay, and this is really, as I will go back to this later, but this is really something, one instance of resurgence. And what is, again, important is the position domain. So remember that in the paradigm of Borel-Laplace, it's always hard somehow to go up and take the Laplace transform. Well, if we are interested in understanding the Stokes phenomena, once we can understand how to do the analytic continuation of maybe that just one germ of function, then the information is there. So we don't have to really understand whether we can Laplace transform. We can stop one step earlier. We can stop in the position domain and find the information we want. I stop here. Thanks.
So,
important to consider everything that's for the function, because even the same okay, those computation, but we're not aware. It's fine to go down in some places.
Yes. I mean, I make this choice only because of this relation. But in fact, yes, you can just take the modified Bessel and replace M on N with a complex parameter nu, or maybe mu. And everything works exactly the same. I mean, you can do the same computation again, because you will find the hypergeometric function with, okay, different parameter. This is also what, I mean, if you take a look at that paper, we have the example for the generic Bessel. And the picture doesn't look exactly like, so if you go here, doesn't look like the previous one. Oops. Doesn't look like these, are more in this style. I think probably is also there. Yeah, if you uncomment this thing, Bessel zero cylinder. No, sorry, not Bessel. No, these are different. Sorry, no, we don't have it here. We have higher area corresponds to slightly different function here when you take higher power. So typically you have not Tn. Area can be, a way to write the area function is taking f of t of this form. And how was written in the other program, you can also take higher area, let's put an r, and you would have r plus 1 divided by r plus 1 minus t. So this is also some function that has been considered in this paper. But yeah, you are perfectly right. I mean, the same computation work for more general Bessel equation. And in fact, maybe I haven't said that, but you can also take the asymptotic expansion of this Bessel equation, and if you expand it, you will get back the formal power series solution that we compute at the very beginning. So if you take, depends of course which contour you take. So if you take C1, one corresponding to this, you will get back phi1 plus phi1. The phi1 tilde. So you can compute asymptotic expansion. You can compute asymptotic Z, and you get one of the formal power series. And you can also, yesterday I mentioned something about the fact that this is morally a Laplace transform. Well, when you write this explicitly, we did the computation, and you can take a look in the paper or do it yourself. You can really see that this Bessel, or maybe let me just write here, K M on N Z is in fact the Laplace transform, more or less, of theta 1, phi 1, where the phi 1 is the same, or maybe phi 1 at, I mean, they are all equivalent. So you can really do this computation explicitly using, again, property of hypergeometric function and the explicit expression for this polynomial, and you can check that everything will work nicely and is consistent. Okay.